Okay, so in this problem, what we have is we have a box or a block that's up here on this hill. So we have a hill, right? So this is flat, and then it goes down, and then it's flat again. Okay, and then the height of this hill is h. We don't know what it is, and that's actually what we're supposed to find is h. So initially, this block is up here at the top, and it is at rest. So it's at 0 meters per second. Okay, and then as it goes, then it somehow it gets released from rest. It comes down this hill, and then it accelerates, and then it comes down here at the bottom. All right, and here at the bottom is 4 meters per second the velocity. So we went from 0 to 4 meters per second due to this hill. Okay. Now there is friction here on this slope, and the coefficient of friction. Just write that. It's I'll try it over here. Mu sub k is equal to 0.15. Okay, so that's the coefficient of kinetic friction between the box here, the block, and this slope. Okay, so what we're trying to find out is h. What is h? Okay, so because this problem involves energy, we're going to use energy to try to solve it. Okay. So the first thing I would like to do is at the top of this hill, right, when it's 0 meters per second, all we have is potential energy. There is no kinetic because it's not moving at all, right? So there's no velocity. So there's no velocity. It's all potential. So initially, at the top of the hill, all we have is just potential energy, right? That's it. Then it's going to go down the hill, and then it's going to be at the bottom. At the bottom of the hill, it's going to have no potential energy because the potential energy is effectively between here and here, between these two locations. And so once you've descended down to here, you have no potential energy because if you compared it from here to say here, yes, there is, but we're only comparing the potential energy from here to here. And so from here to here, yes, there is some, but once it's down to here, it's gone. Okay, so there is no potential energy. So remember, energy has to remain the same in the system. So this is step one right here. This is step one, and this is step two. Step one is at the top of the hill, and then step two is at the bottom. So at the bottom of the hill, down here, this is the potential energy, which is 0. I'm just writing a line here just to illustrate nothing. But then what happened to the potential energy? Well, if there was no friction here, then it would be converted completely into kinetic energy, right? So then PE would be just KE, all of kinetic. But because there's friction here, then friction is consuming some of that energy. So some of the energy, I don't really know how much, is due to friction. And then the rest is going to be kinetic energy. So we have potential energy at the top of the hill, and then once it's at the bottom, it's now been changed by work. By what? Work. So maybe I'll just use a different color for that. And I'll say work happened. Right, work happened on this potential energy, and now we have frictional energy, or like the internal energy of the atoms in this box, and kinetic energy, and then no potential energy. So work changed this into this. Okay, so what's potential energy? Well, potential energy is just mass. Try that again. Mass times gravity times height. Do we know mass? Yes. It's 0.42 here at the top. Do we know gravity? Yeah, 9.8. Do we know the height? No. We don't know that. So out of this part here, change it to this. We don't know this. We don't know this. Okay. And then kinetic energy is this guy here, which is what? Kinetic energy is 1/2 mv squared. Do I know do I know half? Yeah, that's half. Do I know m? Yeah. Do I know m? Do I know v at the bottom? Yeah, it's 4. So we'd actually know all of this. We actually know all of this. Okay, and so if we do that, if we do 1/2 times mass, which is 0.42 kilograms, times velocity squared, remember it's at 4. Right here, 4. It's at 4. 4 squared, of course, is 16. 16 times your mass. 16 times 0.42 times a half. Well, you could say 16 here, because 4 squared is 16. Half of 16 is 8, and then you could say 8 times 0.42, and you get 3.36. So this ends up being 3.36 joules. So I don't know how much energy the potential energy is, but I know the kinetic energy is 3.36 joules, right? And let's just write that here as well too, 3.36. Perfect. Now, friction. This one's going to be a little bit tricky. Okay, so friction. So what I need to do is I need to figure out what the friction is of this guy. So so first of all, it's at an angle, right? It's at a 52-degree angle, and so it makes the calculations a little bit tricky. So what I'm going to do is I'm going to kind of flatten this out. The math ends up being the same, but you have to be aware of what you're doing. Okay, so I'm going to make this thing flat instead of at a 52-degree angle like this. And if I make it flat, then the normal goes up, and my the frictional force is in this direction. The friction due to kinetic friction is in that direction. Okay, and then the weight. Well, where's that at? Well, that's here. mg, weight, mass times gravity. Okay, so just to recap, this is the same as this. I just rotated it. I rotated this thing clockwise. I rotated it clockwise. How much? 52 degrees. So, yeah, and so this is 50. So right here is 52 degrees. And of course, we have like a little arrow here. We can do that. We have a little arrow here. We can do that. Okay. So anyway, this is the same as this. I just rotated it, like I said, 52 degrees clockwise. All right, so what's N? I don't know. What's FK? I don't know. But I do know mg. So mg, of course, is mass times gravity, 0.42 times 9.48, right, equals 4.116. 4.116 newtons, because this is a force. So because I know that, what I can do is, because I know this, because I know the length of this thing, I can say this side is, because it's opposite, I can say 4.116 times the sine of 52 to get this, and the cosine to get this. So if I do that, I'll get 3.243 newtons to the left, or in this case down. That's what it is, going down. And like that's this way, which is this way, which means this way, which is down the ramp. Okay. And okay, and then this is, so that was 4. This is 4.116, which is this, times the sine of 52, which will give you this. If you do cosine of 52, you'll get 2.534. 2.534 newtons. Okay, now that I know that, now that I know this, the normal force has to be the same as this. If it wasn't, it would come off, right? It would be accelerating or moving in this direction, and it's not. So this has to be the same as this. That's Newton's first law. If the forces are balanced, there's no acceleration. Okay. So therefore, this is 2.534 newtons. And of course, then our force now is equal to mu sub k, your coefficient of kinetic coefficient, times the normal force. Okay, times normal. Normal is 2.534. Mu sub k is 0.15. If you do that, if you multiply that together, you end up with 0.38. 0.38 newtons. Okay, so now I know the force. Now I know this force is it's going this way, right? It's like pushing or pulling whatever in this direction. But the force is going in this direction. But this is going in this direction. So, but it is parallel. So the force and this object are moving in the same plane, in the same line. They're moving in the same line. They're both parallel to each other. It's just this thing is moving this way and the force is moving this way. Therefore, the force is going to be doing work, but it's negative work. Instead of helping it out, it's going to be hindering it. It's going to be slowing it down, so it's negative work. Okay? So, in order to find the work, or you could think of it as like energy, work is equal to force times distance. And because they're both in the same plane, they're both parallel to each other, you can just multiply them. So the force, of course, we just mentioned is 0.38 newtons. And the distance is, so what's the distance here? Well, it's this right here, right? It's this distance here. Now, do we know what this is? No, we don't know what it is. But we do know that this is 52 degrees and this is h. And we don't know what this is. Okay, so let's figure out what the hypotenuse is. The hypotenuse is, what I could say is that the sine of 52 degrees is equal to the opposite over the hypotenuse. And opposite of 52 degrees is h. And the hypotenuse is the hypotenuse. So what I could do is I could just flip these guys, and then I could say the hypotenuse, which is what I'm looking for, the length of it, is equal to h over sine 52 degrees, right? That's what I'm looking for. So that's how long it is. So this thing, the length of this thing, which is the hypotenuse, is h over the sine of 52. So if I come back down here, the work is force times distance. What is the distance? Well, the distance is h over sine 52 degrees. Okay? And so now I know friction. So friction is now, I'm just going to put this here. So this is 0.38 times h over sine 52. Sine 52 degrees. Okay? So, I have this. This is the potential energy is mgh. Friction, the energy that went to friction is this. And then our kinetic energy is this. And the potential energy is 0 joules. Okay? Now I can just write an equation. This should be the same as this, right? This should equal this. This should equal this. So, mgh should equal, let's do friction, 0.38 times h over sine 52. Sorry, sine 52. Plus our kinetic energy, which is 3.36. Okay? So now what I want to do is I kind of want to reverse the 3.336 and the mgh. So I'm going to go negative 3.36 equals 0.38 h over sine 52 minus mgh Okay? And now what I'm going to do is I'm going to pull out the H. So I'm going to say negative 3.36 equals H, and I pull it out. And I should have 0.38 over sine 52 minus mg. Okay? And now, I know what mg is. Mg is just mass times gravity, which is 4.116. So this is effectively 4.116. And now what I can do is I can just divide that out. So that goes away over this. So that's 0.38 over sine 52 minus 4.116. So it's this equal to H. And if you do that math, then you'll get H is equal to 0.92. 0.92 meters. Okay? And so so that's basically it. So the main idea here is that you're looking for the total mechanical energy in the system, which is potential plus kinetic. And up here, it's all potential energy. Down here, it's really all kinetic. At this point here, it's all kinetic, but we did lose some energy due to friction, right? This was non-conservative, so we did lose some energy due to friction. So this is the energy we started out with. Think of this as a battery. All right, this is our battery, and we lost, however much percentage of our battery due to friction, and the rest of the battery went to kinetic energy. So this energy and this energy, this energy equals this plus this. So, yeah, and so that's basically the conservation of energy basically states in a system, in a closed system, the energy won't go up or down, it'll stay the same. And that's true. The energy did stay the same before and after. It's the same energy. This energy equals this energy. And all that happened was and that transformation happened because of work. Okay? All right, that's it.